please feel free to interrupt anytime if you have any questions or anything like this. So this is mostly an overview of derived Mickey functors. I will probably very briefly mention some things I've done myself with some other people, but I just want to give a story about where these things. Sorry, there is some motorcycle here passing by. I'm just going to give a story where these derived Mickey functors came from, and and
it's a biker gang.
yeah, it's like 5 motorcycles in a row or something. Sorry for that. All right. But before I tell you what derived Mickey functors are, I should start with some small overview of classical Mickey functors. If you can't read my handwriting, also please let me stop, and I'll try to improve it. So I will give just one version of this. So a G is always a finite group here. And I will be very often sloppy with my definitions. So if you want to interrupt me, also feel free, but then I will just tell you I'm sloppy. So G is a finite group. And what I want is to consider the category. And I want to make a point here, one category, a normal category, which I want to denote like this, maybe like boldface A. It's the effective Burnside 1 category, so effective Burnside category. And what is this? Objects here. Objects are finite G sets. And morphisms from X to Y are just equivalence classes of these kind of spans, which you probably have seen before as well, of maps of finite G sets and modulo some equivalence relation. And this equivalence relation is identifying a span like this of G sets with another span like this. If there is a equivariant bijection here that makes the both diagrams commute, and this is our equivalence relation. So this is what you divide out when you consider. So you consider morphisms are not just these kind of spans, but equivalence classes of this type of spans, and these are even abelian monoids. Abelian monoids with respect to a disjoint union. So you can put here a disjoint union of these Z's gives you an abelian monoid structure. In fact, this category is so-called pre-additive category. So this disjoint union can be also done on objects, and this is both product and coproduct. So this makes this into pre-additive category. Pre-additive, or I don't know. Some people use different terminologies for these things, but let's not go into that. So one thing you could do, which is unnecessary in this talk, in fact, one could also consider group completion of this category. Group completion, like in group complete these morphisms, and then this is sometimes just denoted by AG. And for the purposes of this talk, it doesn't really matter which category you're gonna work with. Okay, and now, so definition, and this is a good old classical definition reformulated by many people in history. So Mickey functor, G Mickey functor, is an additive functor, functor, let's say M from this category. And I want to always use this boldface because later I will not Matt BB font. I will later not to do it. So to just too many A's in this talk. So we have this kind of functor. So an additive functor like this is a Mickey functor. So that's one of the definitions you can give of Mickey functor, a quick definition. And before I tell you some examples, so that we just get a bit of a feeling what am I talking about here. One thing is that this functor is additive, and every finite G set can be written as a disjoint union of these G mod H alphas for some finite index alpha. Therefore, the values are completely determined by just saying what happens on by values of m at these G mod H's. And the rest is just forced by additivity. Now, if you know more traditional definitions of Mackey functors, there are special type of spans which also tell you that there are certain kinds of morphisms here between these mg mod h's, the so-called transfers and restrictions and conjugations. But I don't really need them in my talk, so I will not go into this. But you can recover these morphisms by looking at special type of spans like this, and this factoriality in these spans automatically defines these things for you. And then the fact is, if you impose certain relations between these things, this also recovers the span description if you prefer that one. Okay, so this is sort of the super quick definition of Mackey functors. Now examples, the ones I care about, at least in this talk. I mean, maybe the first example I should mention is also the first example I've ever seen in my life of this as a student. If G is a finite group, again, and A is a ZG module, And then for example, a correspondence assigning to G mod K, for example, if you assign to it a group homology of whatever star you want to fix of K with coefficients in A, this has a structure of Mackey functor. So this is a Mackey functor, naturally a Mackey functor. Now, obviously, you have to specify all the factoriality as well. And most of the time, I just won't do this in this talk. I will just mostly tell you where this G mod H goes. Like I will always tell you what this correspondence is. So what does it do on objects? And then all the other structure is sort of meant to exist as well. Okay, so that's the first example maybe. So you see that it shows up classically in homological algebra in other places. So then the other one is, of course, the representation ring. You can send this G mod H to the representation ring of H. And this is whichever representation ring you want, real or complex. And this is also a Mackey functor. This has the Mackey structure. And this is probably one of the original Mackey functors also considered in representation theory by Mackey himself. This has the structure of this induction and restriction and all these things. And if you assemble all these things together, this makes this exactly into a Mackey functor. Third example, very similar to this, is something also probably Mackey considered originally. So I will denote this by BH, even though this thing is denoted mostly by AH. But I have too many A's in this talk, so I need to choose a different letter. So this is the Burnside ring. This is a Burnside ring Mackey functor. And this assigns to every G mod H a group of finite H sets with respect to disjoint union. So if you don't know what it is, it's a combinatorial version of the representation ring, which you probably know what it is. Now, fourth example is more serious, sort of more fancy example. So which generalized everything before I said. These are equivariant cohomology theories. Equivariant cohomology theories, and this is sort of this ROG graded sense. I mean, I will in a very sloppy way tell you what this is. You have to be very careful while defining these things, but I will be very very quick. So what you can do is you can consider this type of, you can consider GCW complexes, so pointed GCW complexes, pointed GCW complexes, so equivariant CW complexes. Again, I'm not exactly defining what these are, but I'm hoping that you have seen it. And you can consider contravariant functors. So you can consider such a set of data. So what is an equivariant cohomology theory? It's sort of a set of these type of functors, contravariant functors on this thing, going to a billion groups for every real, let's say for every real representation of finite dimensional real representation G, satisfying sort of usual axioms like excision, additivity, homotopy, the usual things you know from non-equivariant situations, long exact sequence. I don't know, I mean, probably overloaded already these axioms. Some of them follow from some others, but the main thing it satisfies, which is very different from non-equivariant or so-called naive, not ROG graded situations, and I'll give it a special name. Star here is the suspension isomorphism. And this suspension iso involves representations. So first of all, let's define what's S to the V, and this is 1-point compactification of the representation V, and then the suspension V of X of a G space is just a smash product of this V with a space X. And now what the suspension isomorphism asks us is that you have these type of isomorphisms that you go into here, and it gives you that. And this condition is enough to have a consequence of some structural consequences about the coefficients of this cohomology theory. Now, under these conditions, the correspondence G mod H goes to the zeroth cohomology. And maybe I want to denote this by G here because just to make a point that it's an equivariant sort of cohomology theory. So you plug in inside there G spaces. So this correspondence, zeroth cohomology of this, for example, this has a structure of Mackey functor. So this is again a Mackey functor. And all of the examples I told you before are pretty much special cases of this. Now, that's the sort of cohomological viewpoint about Mackey functors in some sense, like a covariant cohomology viewpoint about them, the ROG graded sense. But the fifth one, and this is the most general example of Mackey functors I will ever mention, and probably you can ever mention, from these kind of cohomology theories, you can easily end up with G spectra, or the so-called genuine G spectra, but I will not consider any other type of G spectra anyways in this talk, so I'll just call them G spectra. So the thing is that these kind of cohomology theories, under certain conditions, have some Brown representability. So that means that given such a cohomology theory, there is for every V a G space E sub V, such that it has this representability condition that if you calculate the cohomology of X, that's just homotopy classes of maps from X to E, B, G. And now suspension isomorphisms, and again, this is a bit sloppy because we can't quite right away apply here Ioneda, but there is a way to yoga this, and then it's again some sort of Ioneda. The suspension isomorphism corresponds to maps like this, omega W E V plus W, where this omega W is loops with respect to the representation sphere. So exactly speaking, it's just this V plus W. Now you can of course adjoin this if you want, and this is more traditional way of defining this kind of G spectra. Now this is a very old school definition of a G spectrum, and it's not a complete definition. So with this you arrive what a G spectrum is. The modern definitions, of course, are using some other technologies, which I will, by the way, mention at some point in this talk, using, for example, infinity categories. But again, like there are various ways of defining this. So definition, a G spectrum, and this is not a precise definition, G spectrum, but good enough. Yeah.
So you meant EV to loop W, V direct sum W as an isomorphism or a weak equivalence or something, right? That's what you meant by suspension iso.
Here, I mean, yes, but not here anymore, right?
Okay, yes, that's right.
But here you are absolutely right. I should have said this. Yeah, thank you. Yeah, I just like being sloppy, of course. Yeah, but thanks. You are right. Suspension iso gives you a weak equivalence. Now, a G spectrum for me in this talk is, because I'm not going to ask anything extra on this thing. This is why I was kind of like to swap this under the rug, but you're right. So a G spectrum is a collection of G spaces for every G representation, and like that, of G spaces, together with these kind of structure maps like this, for every V and W, satisfying lots of axioms plus some axioms. But we don't need these axioms in this talk. So, but in order to get an idea, this is sort of the equivariant generalization of the usual spectrum, what you have seen before in your life. And now the good thing is that if you have such a G spectrum, you can define its equivariant homotopy groups. So I will define for you pi 0h. I will not define for you what's, so I will usually denote this by E, and I will denote pi 0h to be the zeroth equivariant homotopy group of such a thing. And that is given by homotopy classes of maps from this representation sphere I defined into EV. And then you take H equivariant homotopy classes of maps, and colimit can run on bigger and bigger representations, finite dimensional representations. If you want to make this precise, then you go to these universes, which I do not want to do. And V can be either all H representations or all G representations, because all G's representations, restrictions of G representations are cofinal in H representations. So it doesn't really matter. And so it turns out that this correspondence is also giving you a Mackey functor, and this is the most general Mackey functor you can get, because every Mackey functor can be realized like this. So this is also a Mackey functor.
How is it more general than number 4?
It's absolutely not general than number 4. It's just literally a reformulation of number 4.
Okay.
Thanks for making that point. So this is just non-cohomology theory way of describing, after representing cohomology theories, describing what this Mackey functor was, which I was talking about before. So that's a very good point.
Okay, thank you.
Right, but now, so these G spectra are exactly the things we want to study, and the Mackey functors are sort of there to study them, at least for me. And this should be considered as an analogous thing as if you have given a spectrum, then abelian groups are there to help you to study them. So let Mg now denote the category of Mackey functors. So it's the additive functors from this Burnside category I was talking about of spans into abelian groups. So this is the category of Mackey functors. Category of Mackey functors. And this is a nice abelian category. It's abelian, enough projectives. And later I will also say, maybe I can right away mention this also as a tensor product, the so-called box product. So it's a symmetric monoidal. So all the good things, but it has a bit of a issue that the homological algebra is difficult in here, because it's infinite homological dimension. And there's very rarely that Mackey functors have actually a finite cohomological dimension. I think John Greeley says some funny papers about this, that like very often the dimension is just infinite. I mean, obviously there are some projective Mackey functors as well, but I'm just saying it's not as easy as homological algebra of abelian groups. Okay, so now what you can also do, you can also consider SPG, and this is for me the category of G spectra. Category of G spectra. Now, whoever you are in the audience, either think of a homotopy category, or think of a model category, or think of an infinity category. It's your choice. But I mean, unless you are giving some very specific technical talk, Rune Hauksing once taught me that I should always give my talks model independently. So should always give a freedom of choice to people, what they want to think about, what objects you consider. So I will not specify what kind of model of G spectra I'm looking at it here, at least right now, maybe later. Okay, so this is my category of G spectra. So category of G spectra. And so we have this functor I was talking about before, this Mackey functor pi 0, which was defined here. So this correspondence I want to denote by this. And this is now a functor going from G spectra into Mackey functors. And this is now, obviously, there are higher homotopy groups of this type as well. You can write here pi star. And this is a good enough invariant to detect weak equivalences, for example, in G spectra. Now, so this is how Mackey functors are related to G spectra in sort of very intimate way. But also, there is another functor in usual stable homotopy theory. We also have, so this is an analog of usual homotopy groups, but we also have usual singular chains functor from usual spectra into chain complexes. Or maybe I should denote these chain complexes as a derived category, and sort of so we have this functor from spectra into the derived category of integers, which can be taught as the category of chain complexes of integers, and then inverted quasi-isos. And then again, what you want to think about, if you want to think in terms of homotopy categories, this is the classical localization, otherwise it's infinity categorical localization. So these are singular chains. And the thing is that this singular chains is exactly the kind of a functor that naturally lands in this derived category of Z. These singular chains, of course, generalize the classical singular chains of spaces on the category of spectra. And most of you probably have seen how this is defined. And there is an analog.
I have a question.
Yeah.
Can I think of this map as smashing with HZ?
Yes, that's exactly what it is. But of course, I want to make a point that you can actually also define a chain complex if you want, and you don't have.
Yeah. Okay. Yeah.
There is a model like this. You can define it.
Okay.
So there is an X-variant version of this, which, because you asked, can be taught as smashing with the Eilers-MacLane spectrum of the Burnside ring, but I don't want to go into details. So there is an equivariant version of this, which looks as follows: that it's just is some equivariant Bredon chains basically. And again, I don't want to define this thing, but I will just tell you what it is. So there is this functor, analogous functor, that lands into the derived category of Mecke functors. Now, Mecke functors, I told you, is a nice abelian category, and you can do in this situation, you can always do also a derived category, which is then just chain complexes of Mecke functors, and then quasi-isomorphisms inverted. Isos inverted. And there is a way to define this thing using some thing called Bredon chains, which of course will take me now a lot of time to really define, so I don't want to do it. But this functor, maybe we should call this here. So when G is trivial, then of course this recovers so this is the case G is equal to trivial. This recovers the usual singular complex. But now this functor has some issues. So first thing is, first of all, it's actually not as bad when it comes to monoidal structures. So as I told you, Mecke functors have a monoidal structure, but G spectra also comes with a smash product, or which I want to just denote by tensor product in this talk. So it's a symmetric monoidal infinity category, and same about this derived category also comes with a this kind of a box type product, and this functor is lax monoidal. This is lax monoidal. So there is no issues about this. But the problem of this functor is that it's not compatible with something very important in equivariant stable homotopy theory, not compatible with geometric fixed points. And I will say exactly now what that is. Geometric fixed points. And my goal in this talk is to somehow tell you at least my version of like how these derived Mecke functors even showed up first, and what's the story behind it, and what was the motivation of Kaledin to actually define them. And so therefore this is important to understand this point here. Okay, so now what are geometric fixed points? I mean, obviously most of the people in this audience know it, but I should give my version of this functor. So the idea of geometric fixed points is that there is essentially unique in terms of infinity categories. Sort of the space of such things will be sort of contractible. But again, if you work with homotopy categories, then there is a unique functor that goes from G spectra into spectra with the following axioms. So the first one is it commutes with sequential colimits. Commutes with sequential colimits. So SP is a spectra. I should have maybe written this explicitly, but if SPG is G spectra, then I think you are guessing that SP is just spectra. It commutes with sequential colimits. Second is it commutes with the suspension spectra. So every space, of course, comes with a associated spectrum. I mean, I don't want to define that. Then it is monoidal, strongly monoidal. So it actually is commuting with tensor products. And finally, I mean, I think these already determine it. I mean, when I write also functor here, I mean, it preserves weak equivalences, but it actually even detects weak equivalences. I think this is a bit, you don't even have to say this now, but I will just put this as an extra property. So something is a G equivalence, so equivalence in SPG, if and only if its equivalence on all geometric fixed points for every subgroup. So if the induced map is an equivalence uh, subgroups H. All right. So this is the geometric fixed points. Now there are specific models, whichever you like, you can write down for this, and it's very easy to write this down, but I don't want to do that. One immediate consequence of this is that this functor is a localization, which means that if you take G spectra and you kill inside here a tensor ideal. So you take a subcategory generated by these things under cofibers and coproducts and extensions and retracts, and then you sort of close it up also on the tensor product. If you generate tensor ideal by suspension spectra of proper orbits, so H is not in G, then it turns out that this is actually equivalent to the category of spectra and non-equivariant spectra, and the one that realizes this story is exactly this geometric fixed points. So that's one of the applications of this consequences. The other thing is that there is also for every G spectrum the associated usual derived fixed points. So usual fixed points, like honest fixed points. I mean, after good enough derivation, like after replacing it by an omega spectrum. And this is definitely not the same as this thing. And there's a major difference between these two. The only role of this thing is that one of the main roles of this thing is that if you take its homotopy groups, this is a usual spectrum. These are the equivariant homotopy groups I was talking about. So geometric fixed points does not see equivariant homotopy groups, but it's still good enough to detect equivariant homotopy types and has all the nice properties you expect from fixed points, which these guys do not have. I mean, they are very tricky. For example, for the sphere spectrum, which is a suspension spectrum of G mod G, which is the S0, this is huge. I mean, this is sort of a suspension spectra of some classifying spaces of these finite groups, all conjugacy classes. Whereas if you take geometric fixed points of the sphere with a trivial action, it does behave like what the actually geometrically fixed point should do on a trivial action. It just gives you the sphere back, and it's in general true about any inflated thing. So that's the point I want to make. And because somehow this functor here is more compatible in a way with these genuine fixed points rather with geometric fixed points, the main problem what this functor has, this singular chains I was talking about, that takes values in this derived category of Mackey functors, it doesn't really see the geometric fixed points. So on the side of spectra, I have this nice functor with all these properties I told you that lands into spectra. And there is also a singular chains here with which goes into derived category of Mackey functors with respect to trivial group, which is the same as derived category of Z. But there is nothing here that will make this ever commute. You can make this statement precise. I think we even make this precise in that work with Bernd Sanders and Christian Wimmer. But I will mention this in a second. So one of the main justifications why there is nothing like this here, this is not the same. Like, as I told you, this was localization, but this is not a localization of this category of derived category of Mackey functors modulo stuff generated by singular chains of G mod H's, G mod H pluses, let's say like this, where H is the proper subgroup. So if you kill these kind of orbits in here, you're not going to get derived category of Z, but you're going to get something else. Actually, what you're going to get is I think just the derived category of the geometric fixed points of the Eilenberg-MacLane spectrum for the Burnside ring, which is actually a derived category of some graded algebra rather than derived category of Z. So it's something much more complicated. So therefore, this does not exist. And what Kaledin wanted, Kaledin's motivation was to construct an algebraic version of geometric fixed points. Sorry, sometimes my system issues.
Irakli, can I roll back and ask you a question for my personal understanding?
Sure.
If you go back, like in your previous display,
Yeah.
Just above the diagram, what you wrote.
Yeah. Just a second. I'm having some. Yeah, I think I fixed it. Yeah. Yeah.
So the geometric fixed point that you mentioned is picking up one of the components of the actual fixed point for the sphere spectrum at
Right,
least.
right, right, right.
And
Yes.
so now you're saying that in this diagram, so I'm thinking from my point of view, smashing with HZ, and
Yeah.
here you're gonna smash with HZ, but when you take the geometric fixed point, you're
Right.
actually smashing with geometric fixed points of HZ, which is not HZ itself.
No, I'm not smashing with HC. I'm smashing with geometric fixed points of Burnside ring, Eilenberg-MacLean.
Oh, okay. Because of the
That
pi
is,
zero, because of the
it,
pi zero. This is much
it, is,
bigger. Okay.
it is not much more different than geometric fixed points of HZ, to be honest, in most of the examples I know. But again, this is by far not HZ. Like,
I mean,
it's,
Burnside ring is bigger than Z, so it
I mean,
is.
this is usually gonna be a graded ring in these situations. Like, it's gonna
Uh,
be having everything in every.
so
And
then my follow-up question would be, can HZ, is there a projection map to HZ, or does HZ split off from this? Or maybe HA split
I
off
think,
from
I mean, these things are usually say take cyclic group of order two, then these things
true. Yes,
usually come.
that's why I'm asking.
When you take homotopy groups, these things are usually, let me see. I think if you do Z itself, geometric fixed points of Z with cyclic group of order two is polynomial in F2 in degree two.
Yeah, I see.
And
Okay.
they do split as spectra because they are some Eilenberg-MacLean type
Okay.
spectra.
Okay.
But and I think for integers itself, I think there is one copy of Z actually staying around there because you kill the transfer only.
Okay.
But then again, I don't think this helps in this situation. Yeah, but
No,
it's
I now understand the problem that you're tackling. Okay.
yeah, yeah. So I mean, I didn't tackle this problem. It was Khaledin who tackled it. So what Khaledin now said is that you need to modify this category in such a way that you have something like geometric fixed points on algebraic side. Now, why did he care about this question? Not just because he was big fan of equivariant stable homotopy theory. So he had this project on topological, maybe he is, I don't know, but at least his motivation was topological cyclic homology. And he was working on this stuff on Terama beta complexes and things like this. So in this topological cyclic homology situation, you often look at spectra, and let me not specify with what action, but usually it's either S1 spectra or spectrum or CP infinity spectrum. One of those. You look at these things so that the geometric fixed points of X is equivalent to X itself. And what Khaledin was after, because of some of his constructions, was to see sort of what's the algebraic version of this algebraic version of cyclotomic spectra. And that's why he wanted to define some kind of chain complex type things where the geometric fixed points sort of make sense so that he could actually take advantage of maybe some extra HZ linear structure around to actually deal more easily with those type of cyclotomic spectra than the ones that classically exist and are kind of difficult to compute. And but he couldn't do it because the usual Mackey functors, as I told you, do not admit anything like this. So there are no geometric fixed points here, so we can't even do this with usual derived category of Mackey functors. So instead, he defined derived Mackey functors, which solved this problem. Derived Mackey functors. Um, Right. Now, don't get confused. Derived Mackey functor is a different thing than derived category of Mackey functors. So derived Mackey functor now will be a different type of object. So now how he did it is that instead of this AG, which we considered, which was this effective AG, so instead of this, consider a very similar category, but a 2-1 category. Consider a 2-1 category. A 2-1 category with the same objects. So to one category, and I will denote it by A twirl G. This is sort of an intermediate category I will be using anyways, so I don't have to introduce a special notation for this. So objects here are, again, finite G sets. Morphisms, one morphisms are spans. I'm not saying anything like, okay, I'll write it like this. I should have written X and Y. But, these are these kind of spans of finite G sets, but I'm not saying it's an equivalence classes. And also what he noticed was that for two morphisms, you consider those isomorphisms which we were dividing out before, you take them into account. So two morphisms are these type of morphisms between these kind of spans. These are the two morphisms. And here isomorphism. So he considered those isomorphisms which we divided before into a structure of a 2-1 category. And it's a 2-1 category because two morphisms are invertible. And now what he did, he wanted to put all this information now into homological algebra because he wanted to work with Mickey functors. So what he looked at, he considered a new category, chains over this A twiddle G. And what is this category? Again, objects. Every category I will consider today, objects are finite G sets. Finite G sets. But now morphisms from say X to Y, these are what you can do. This is a 2 category. So you can take a category of morphisms from X to Y. You can look at its classifying space, or you can take its nerve, depending on what model you want to take. And you can take its singular chains or cellular chains or simplicial chains, one of those, just usual chain complex of this space. And this is your morphisms from X to Y. Now, of course, the first intuition is that this is supposed to be a DG category, or maybe at least when I was reading it, the first wrong impression I got was like, oh, this is going to be now a DG category. But it's not a DG category, so this is not a DG category because the composition in this 2-1 category is not strict of the one morphisms. It's only strict up to, it's only weakly associative up to those isomorphisms, right? So what you really get is an A infinity category. So this is A infinity category. So not a DG category, but an A infinity category in the sense of Stashev and Kadeshvili and some of the others, and structure that was considered in the 60s and 70s and still very popular. So the homotopy associative, higher homotopy associative chain complex multiplications. It's an A infinity category. And finally, what he noticed is that if you take this A infinity category, you can consider A infinity functors. So it's functors that respect this A infinity structure, which are additive because again, this category is additive with respect to these disjoint unions, this A twiddle G. I mean, everything comes with this disjoint union additive structure. If you consider these additive functors from this funny A infinity category into the DG category, or also can be considered as an A infinity category of chain complexes, and then invert quasi-isos, appropriate quasi-isos inside here, make again some sort of a derived category. This is this category of derived Mickey functors. So I will denote this by dMacG instead of just dMG. So this is the category of derived Mickey functors, original. This is how he defined it in that big paper in Moscow Math Journal. I think it's around something like end of 2000s when it happened, like 2009 or 10 or something, when he defined this. Now he also has another description of this category in his paper, which uses some sort of a Waldhausen type construction, so a Stott type construction, which is slightly simpler than this definition, but it gives a bit less intuition why the next thing what I will say is related to this stuff. One thing you immediately notice when you look at this,
What kind of object is that now? You're considering it as a...
I mean, what he did is just one category. So what he really did, he really looked at functor category, honest A infinity functor category, and he inverted, localized it in classical Gabriel-Sisman way. And he just got a one. So this is actually homotopy category of some infinity category as well, which I will just mention in a second. But originally he only looked at it as a one category, so homotopy category or something. Yes, but it's a good question. Thanks. But what he did, he managed to at least solve this problem with this thing that like he actually showed in his paper that there are certain type of modified chains with values in this derived Mackey functors, which I will explain soon what it really is. And here, of course, what he was really looking at, of course, again, because Jesper asked, he was also considering on this side the homotopy categories. And here again, the usual singular chains and derived Mackey functors for trivial group is derived category of integers. Again, you just recover it. And here he managed to actually construct this functor and also show that this is a localization, nice localization. So that's what he did, and so that was his goal was somehow achieved. And then he talks also in that paper in some type of cyclotomic spectra, which I will mention at the very end of this talk, how that fits with the modern view of cyclotomic spectra. So he achieved this goal, but of course, I mean, both of the constructions he has in this paper is very technical, and you sort of want to see it in terms of the modern perspective, in terms of these universal properties. And then, I mean, I was lucky to talk to Clark about this many years ago, and also with Dennis Nardin and some others, and people already kind of knew it, that what I will just say now, that should be possible, but nobody, of course, really wrote it up because it's quite technical somehow. And then we needed to do this, and we sort of reformulated this in terms of this Barwick and others effective Burnside category. So yet another category now I want to define without MathBB font now, AGF. This is the infinity one category, which is very closely related to this 2-1 category I was just saying, and there is no explicit construction that makes one from the other. But anyways, this is infinity one category called the Burnside, also effective Burnside category. Burnside infinity category, let's say. So what it really does is that it's zero simplices, which are objects, are finite G-sets. One simplices, again, spans like this. Now I'll say what two simplices are, and then you can imagine what n simplices are. Simplices are something like this. You have something like that, and Z prime here, and here you have Z double prime. So this kind of a double span, but this is here a pullback. So this here is a pullback. This square is a pullback. And n simplices are defined similarly, like you can look at higher and higher versions. Every square is going to be a pullback. So this is an infinity one category, and I should mention here names like Barwick has considered this, and then also Glassman and Nardin and Shah and some others have written papers on approach with this category. But it turns out that if you consider now usual infinity category of, and this has a coproduct here, which is also product, which is again disjoint union. So if you consider infinity category of additive functors on this effective Burnside category into usual spectra, that turns out to be equivalent to the whatever model of genuine G spectra you like to consider. So this is one of the models, one of the ways of defining G spectra in modern days is just this functor category, so-called spectral Mackey functors. Okay, so now obviously if you look at the G spectra is this kind of a thing. If you read Kaledin's paper carefully, and I was lucky enough to do that at some point, early stages of my life. If you look at this thing, this also looks like some sort of additive functor, some sort of a Burnside type category into chain complexes, and this 2-1 category very much looks similar to this effective Burnside category, some kind of a cousin of it. There is actually, I think, an explicit construction called Duskin nerve. And if you apply that to that 2-1 category, I think you're going to get this category actually. But obviously at that time, I didn't know about these kind of constructions. What I knew was what this Kaledin's construction really is, because I think in 2012, and Stefan is here, Stefan was nice enough to send me to Stefan Schwede and John Greenlees were nice enough to organize that I visit John Greenlees in Sheffield for a month. And exactly when I was there, Kaledin actually gave a talk in Sheffield and explained these things. At that time, of course, I didn't understand what he really was talking about, but I remembered what I didn't understand. And so over the years, every time I would discover something similar to what I heard there, I was trying to compare it to that. And so this is how, for me, this thinking about these things started. But then, of course, I talked to Clark and Dennis and some others, and so we got this idea. And then I went to Lausanne, talked to Baron, and eventually turned out we could use this for other things. And so this is how we ended up proving this following, maybe a theorem or proposition. I mean, it contains kind of two versions of this, but I'll mention another version of this afterwards. So this is a theorem which is proved in this paper we wrote. And in some ways, this is just, we wrote this up. I believe that people knew about this before as well, just they didn't bother to write it up. So this category of derived Mackey functors, which I just defined for you with using this A infinity things, this is just the homotopy category of a very similar category as defined here, just additive functors, infinity category of additive functors from this effective Burnside category into chain complexes. Now, I don't want to write down here chain complexes. I want to write down the derived category of Z in terms of infinity categories. So that's what I want to write down. Another version of this is the homotopy category of functor category. I mean, this is just tautological rephrasing. If we, I mean, obviously this is also a result that derived category of Z is the same as the HZ modules. Which maybe first, because Stefan is here, I shouldn't mess this up. I think maybe it was first Schwede and Shipley who proved that. Is that right, Stefan, or you disagree with?
Well, I guess it is similar to your theorem that people knew this and nobody wanted to write it up. I think it's of that sort. Yeah.
All right, very good. Yeah, thanks. Yeah, so, and now I wrote here tensor as well. So all of these things actually work monoidally as well. So there is a monoidal product on these derived Mackey functors, and there are natural sort of deconvolution type products on this side, and these all agree. And the reason why we looking at this is the following. Before that, I just say that this HZ is the Eilenberg-MacLane spectrum, MacLane-Ring spectrum of integers. Ring spectrum of integers. And so we wrote up this proof, and the reason why we did this was to what we wanted is to look at the Balmer spectrum of this derived Mackey functors. So, and that's, I mean, we used this theorem because it was much easier to work on this side rather than on this side. We computed the Balmer spectrum of this thing in this joint paper with Baron and Christian. And I just like want to show you, just in case, the picture. Here is this, oops, that's the zoom. Here is this picture. So what we really show, this is the Balmer spectrum of G spectra for cyclic group of order P. I mean, I don't know how big this is. Can you see this? I mean, I might go in a bit here. So this is the Balmer spectrum of CP spectra, for example, which is computed. But in general, this Balmer spectrum for more general groups is not completely computed in terms of topology. You know, there's some open questions still in topology. And what we showed is that Balmer spectra of derived Mackey functors exactly sees this bottom level here and the top level of this spec. And we showed that this is generally true for every finite group. And we also described always generally the topology on the derived Mackey side. That was possible, as opposed to, because the stuff that really happens here is in the middle, the difficult stuff. And we saw that this easy stuff on top and bottom is just seen by these derived Mackey functors. So that was our motivation to do this. But now there is this nice two articles I saw in Archive, and Baron's gonna talk about these things. They are now studying, this is Tobias Bartel, Baron Sanders, Drew Hurd and Baron Sanders are studying more interesting, even more difficult categories. They are looking at additive functors and examining their Balmer spectra and other features from this effective Burnside category into various other things, like, for example, R modules, where R is some infinity ring, or EN local spectra. The funny thing here is that in the case when n is equal to 1, we wrote this paper with Constanze Reutzheim a couple of years ago, like 3-4 years ago. We were looking at some category of some sort of equivariant in locals, E1 the local spectra. And it turned out that this was also the derived Mackey functors we were looking at. We just didn't know at that time. So that paper, for example, doesn't mention these at all. These are the things which people already study, and there are some results about Balmer spectra of these as well, because these are also monoidal. And Baron hopefully will mention this in his talk. So there are lots of follow-ups of this story. And now I want to quickly mention another interpretation of this derived Mackey functor. So there is this category of G spectra, I told you, is additive functors from this Burnside category, effective Burnside infinity category into spectra. And this comes together with an adjunction. You can always evaluate such a thing at G mod G, the trivial point, which is the same as that fixed point functor I was talking about, not the geometric fixed points, but the genuine derived fixed points. And that lands into spectra. Now this is a left adjoint, which is the inflation, I lower star, this is the inflation. And which is left adjoint to this. And another interpretation of this, result, which is some general infinity categorical statement, actually, which we also prove in this paper. But again, I believe that people already knew about this. But the consequence of that is this proposition, what we proved is that if you consider HZ here, which is a commutative monoid, it's a commutative monoid, you can left inflate that and get a commutative monoid in G spectra. And I will just comment about what kind of commutative monoid is this exactly. So this is an object in here. It's a commutative monoid with respect to tensor product here. You can consider modules over this, and this is also equivalent to this. Its homotopy category, let's say, is equivalent to this derived Mackey functors. And of course, the comparison goes through this category. I mean, we first compare it to this, and then there is some infinity categorical statement that tells you it's the same as just modules over this left inflated Eilenberg-MacLane spectrum. Again, I think this is a more general result. These guys are using this to also work with these kind of categories. Now this is an interesting ring. This is sort of this naive E infinity and not genuine E infinity, if anybody's interested in not genuine. I mean, some people know about these higher multiplications in equivariant homotopy theory with all the norms and all this beautiful structure. So this is very naive one. It's a commutative monoid. It has modules. It has tensor product, but it's not a genuine infinity. And there is a very funny argument using Tate diagonal and some Steenrod squares, which actually can be used to see that this is not a genuine infinity. So it doesn't support some power operations which you would support in general. Now, what are other applications of this result, of this derived Mackey functor business? More applications than what I just mentioned. One of them is this recent theorem, or it's a corollary of the theorem he proves by Achim Krause. And he also gives credits there. And I was trying actually to find this paper, and Jesper is sitting here. I was trying to find this paper by Jesper and Jeff Smith about some kind of Picard groups, but I only could find Oberwolfach report, and I don't know what's going on, you know. No. So I will also mention here Grodel and Smith. At least their results are very related to this. I believe that if you take Picard group of G spectra, which was classically studied by Tom Deacon, Petrie, and some others, and also May, Fausk, and Hu, I think. This thing, Picard group, not the Picard space, is isomorphic actually to the Picard group of these derived Mackey functors. It's actually isomorphic to that. It's a corollary of one of the things what Achim does, but then he also gives you credits. And then in that Oberwolfach report, I saw there are similar things, but I couldn't exactly, grasp exactly this result. But I see probably what he means. Yeah.
I'm not sure we actually get exactly this result, but we get.
But it's related, right? You agree? Yeah. Okay. So that's what you get. So as you see derived Mackey functors also see the Picard group of equivariant spectra, which is which shows that they are also very useful in this sense. Now, again, this should not be super surprising because if you know how Picard groups of G spectra are computed, they are computed all the time using more and more different geometric fixed points and what happens on them. And now we created an algebraic category, some pi0 version of this geometric fixed points, which is compatible with geometric fixed points, and that pi0 Picard spaces agrees in this situation. Again, should not be completely shocking, but you need to prove this. I mean, there is a serious result, which I mean, there are some stable module categories, for example, used in this theorem, and also we were just seeing some Picard groups in the previous talk. So it's not that easy to actually compute such things, and need some machinery which needs to be available. Okay, so another application of this derived Mackey function. And finally, Kaledin's goal. Let's go back to Kaledin's goal. So how did this end up working? So Kaledin's goal was to look at cyclotomic spectra, in derived Mackey functors. And I mean, I'm not sure this has been anywhere written up, but I mean, one can work this out. And it turns out that what Kaledin was trying to consider in this paper with the cyclotomic spectra is something very familiar from modern perspective of cyclotomic spectra. So there is this construction by Nikolaus and Scholze of cyclotomic spectra, at least in the bounded below situation. Anything what I will say now probably will be wrong for not bounded below. So what Nikolaus Scholze considered, they considered this symmetric monoidal category of cyclotomic spectra, let's say for some prime P. So P cyclotomic spectra. P cyclotomic spectra. And now what you can do is you can again consider this HZ, and you can look at this left inflated HZ with respect to all the CPN groups. So CPN equivariantly. In fact, what you really want to do is to take inverse limit of these and consider it as a CP infinity spectrum. But I don't want to go into that. Now, inside this category of cyclotomic spectra, yeah.
In the audience,
Yeah.
CP infinity is what used to be called Z modulo P infinity, just for.
Yeah, this is not used much anymore, but it's also QP mod ZP if you want. Something like that, or yeah. But yeah, Proofer group. I was taught in Bonn not to use this notation, so I'm not using it anymore.
No, Scholze is.
Exactly. Right. So what you can do now inside the cyclotomic spectra, you can also consider modules over this thing. But now this ends up being a cyclotomic spectrum itself. Atomic spectrum. So it's an object, it's a monoid inside cyclotomic spectra, even commutative monoid, and you can consider modules over this inside cyclotomic spectra. So I'm going to write it like that. So as you see, this category is very closely related to the category I was already considering. This was just considering these modules with respect to individual group, but whereas this is sort of considering them with respect to various groups and putting them together. And you can consider this, and this is exactly the category Kaledin was considering as well when it came to the cyclotomic structure. So an object here is some sort of X is some sort of a derived Mackey functor, together with some equivalence that, for example, these geometric fixed points of X is equivalent to X, or some sort of a Tate diagonal equivalently, if you want. There is some sort of a, not Tate diagonal, some kind of a Tate Frobenius kind of thing, which is linear with respect to the corresponding map on HZ, which is highly non-trivial map because it contains some Steenrod squares and stuff like that. So it's linear with respect to that. And this is exactly what Kaledin was after. So now there is a result by Nikolaus and Scholze that in usual chain complexes, you cannot make this happen because there are no Tate valued Frobeniuses in there. I mean, there is an argument about this, but like this Tate diagonal doesn't work. But what you can do is if you make this chain complexes a bit fancier, and that's this derived Mackey functors, then actually it works. And so that's what they somehow figured out. I think I somehow got through now everything what I wanted to say, and yeah, thanks a lot for your attention.
Can you hear me?
Yeah, I can hear you.
Are there any questions?
All right, I see somebody lift a hand, so.
Yeah,
Any
how would you characterize geometric fixed points?
In terms of what?
In terms of your talk, which say, what's the difference between, say, maybe a geometric fixed point and say another type of fixed point from the group operation or something?
I mean, this is what I was talking about here. I mean, maybe I didn't say this well enough. So geometric fixed points is completely characterized by these properties. What I wrote down.
Okay.
I think it's these three properties is enough. If you use this more traditional type of fixed points, which literally would take fixed points of your spectra, but then you should better replace things vibrantly or something like this. So you should better work with omega spectra. Then you are recovering some more bigger things. And I think we already had a question about this. I told you that if you take, for example, those kind of fixed points for sphere, even with a trivial action, because there is some derivation going on here, because you have to first replace it by omega spectra, then you get something much bigger than what you would get with geometric fixed points. So in some ways, geometric fixed points behaves more like traditional fixed points on spaces than the traditional fixed points behave with respect to spectra somehow. For example, these other type of fixed points or homotopy fixed points, for example, do not have these properties. It's only characterized by geometric fixed points. So, and they are unique. Now, if you're asking how you describe geometric fixed points in terms of Burnside categories like this like in terms of this construction here, then I mean, there is a way, of course, of doing it. I just don't want to misuse here the fact that I'm a speaker. I don't want to explain this, but you can look this up in the literature. Like, for example, Dennis Nardin has this in his thesis, for example, and then you can see it there. Yeah, I don't know if it answers your question, but yeah.
Yes, thank you.
I see Ivo has a question, and I haven't seen Ivo for a while, and good to see you.
Hi, Irakli. Nice to see you. Hey, thanks for the very nice talk. I will profit from some of your explanations in my talk because
thank you.
We had some common preliminaries to go through.
Nice.
And so you gave very nice motivation on derived Mackey functors, but well, some people, especially in representation theory, still care about the usual derived category of Mackey functors. So do you have any relationship between the two derived categories which makes some sense?
Yes. I mean, there are some adjunctions, I believe, that come from the fact that the thing is that I told you that derived Mackey functors is modules over this.
Yes.
Whereas the actual derived category of Mackey functors, considered in the infinity category terms, if you want, is modules over HA. Which is
right.
the Burnside ring Mackey functor.
Yes.
Equivalent to that.
So you can construct the.
Now there is a canonical morphism going from here into here, which comes from the adjunction because there is a morphism, I believe, from here. Yes, obviously, if I take fixed point for this, that's the Eilenberg-MacLane for Burnside ring, and there is obviously a ring homomorphism from Z to Burnside ring.
Right.
If you adjoin that, there is a morphism like this. This is a morphism of commutative monoids, I believe, and there is an adjunction. Now, how good this adjunction is, I have not really. It is not super good. I think we have some counterexamples in our paper in terms of like.
To what? Counterexamples to what?
To the fact that. No, not about these adjunctions. What we have is that if you take geometric fixed points of this, then the derived category of that is badly behaved for our purposes. That's probably the only counterexample we have. So we never really studied this adjunction that much, to be honest. but there is one like that. Yeah.
Okay, that's good because I mean, for example, I don't know, is there any hope to transfer the computation of the spectrum, Balmer spectrum?
That's a great question. I mean, I think
because I studied that question a long time ago with Greg Stevenson and Serge Book, and
yeah,
we didn't get too far.
It could be very much related to your results, because if you would study spectrum of this HA, I think you want to again consider some geometric fixed points, because those guys see things, right? Then you will end up into derived category of geometric fixed points of this HA. And that's a graded ring, usually often polynomial in even degrees or something like this. And I think you have considered
Yes.
spectrum.
Wait, I'm talking. Sorry.
You have considered derived categories, Balmer spectra of derived categories of such, if I remember correctly. So
yeah, under some regularity hypothesis, which might come from this being polynomial. Yeah,
they are polynomial and Noetherian as well. I think it's not like
that would be very nice. I haven't really thought much recently about.
So maybe there is a chance. Maybe there is a chance, but we haven't really thought about this approach, this spectrum of this.
Oh, excellent. Well, I will certainly want to look into that. Yeah. Okay. Thanks a lot.
Sure. Thanks for asking. Thanks for attending. Good to see you.
Yeah.